Welcome to Matematika. Today we're going to do the part A of polynomial functions and complex zeros. The first lesson that we're going to do is about zeros of polynomial function. We're going to talk about some terminologies here that are in the zeros of polynomial function. So the term zeros of a function are the input values which make the function equal to 0. A is a zero of f of x if f of a is equals to 0. That is the roots of the equation of f of x equals 0. These zeros or roots appear on the graph of the function as x-intercepts. Like here in this graph, we could say that it intersect at x at this point at 2 and at -2. These are what we call the x-intercepts or roots, where the roots appear on the function and they appear as a x-intercept. Real zeros serve as endpoints for intervals that satisfy polynomial inequalities, as they represent points where the polynomial function is greater and less than a certain value. We're gonna talk about this later on. You see this right side of the function would be greater than 0 and the left side would be less than 0. That is what we mean by greater than or less than a certain value. The next, we have the fundamental theorem of algebra. So the number of complex roots of any polynomial is equal to the degree of the polynomial. Okay? Complex roots are real and imaginary, or we call that as real and non-real. So the real zeros of a function will be the x-intercepts of the graph. Right? Factor theorem. When x equals a is a root of f of x equals a, then x minus a is a factor of f of x. It's of the multiplicity. The multiplicity of a zero is the number of times that its corresponding factor appears in the function. Multiplicities of the zeros in the function will sum to the degree. I underline that because we're going to encounter that later on of the polynomial by the fundamental theorem of algebra. Zeros with different multiplicities look different graphically. All right. So let's have this. Let's visualize how it looks like with the multiplicity. On this graph right here on the left side, a root of multiplicity 1. So if the multiplicity is just 1, it will cross the x-axis. Whether up or going down, it crosses with no point of inflection, because there is no change whether it goes up or down, so there is no point of inflection. With the multiplicity of 2, that usually happen when it's quadratic. Okay, so our quadratic graph looks like that, or it looks pointing down, or point up, or both pointing down. Okay, roots with even multiplicity are tangent to the axis, which means they touch to the x-axis, then change direction, and do not cross the x. All right, do not cross the x. If you try to look at this, if this is your graph right here, it just touch. That means it bounce. It bounce. All right, it turn from here, just turn down. Okay, that is how it looks like. Say bounce or turn. Next is zeros of multiplicity of 3. So 3 is like, it now changes direction, like here it crosses and then it moves to the opposite direction. A root with an odd multiplicity greater than 1 crosses the x-axis with a point of inflection. There is a point of inflection because there will be a change from decreasing to increasing. All right. Let's look at the whole thing in this graph right here. I will make it this big. Okay. This is multiplicity of 3. Multiplicity of 1. It passes through when x is negative 3, so it goes down. And then multiplicity of 2. Look, it just touch. Then it bounce or turn. Okay, it bounce or turn. And then multiplicity of 3, it passes and goes to the other direction. Cross the x-axis. And that is how it looks like. We'll do more on that later. When the coefficient of polynomial meet a certain criteria, a complex roots and irrational roots will come in conjugate pairs. Okay? Will come in conjugate pairs. Complex roots. Complex conjugate roots theorem. If p of x is a polynomial with real coefficient, then a plus bi is a root of p of x, then the complex conjugate is a minus bi is also a root. The term conjugate here, if you remember in your algebra 2, what does it mean when we say conjugate? Meaning that a pair of expression are identical except for the sign between the term. Okay? That means you have to get the opposite sign. So here, if a plus bi, then the conjugate is a minus bi. Right? Irrational conjugate roots theorem. That means there is an irrational value or irrational term if p of x is a polynomial with rational coefficients and a plus square root of b is an irrational root of p of x, then the conjugate is a minus the square root of b is also a root. Alright, let's get to know. If you are given a one non-real zero of a polynomial, find the another zero. Say you're given a 7 plus 2i. So that means you are asked to get the conjugate. So conjugate, same term, 7 and 2i, but the sign is changed. Instead of plus, it will become a minus. So here is the same thing. It will be 5 minus I. 1 minus 5i will become 1 plus 5i. Then negative 3 minus 4i, it will become negative 3. The minus will become plus 4i. Then we have a negative 3 minus 6i. And we have 4 plus 2i. So in other words, if you are asked to find the other root of an irrational number or term, all you have to do is to conjugate the roots, and that is what we call the irrational roots. For each of the polynomial, the degree is listed along with all of its real zeros. So the number of non-real zeros the polynomial has, I want you to go back to this term right here, with which it says that the sum, I will go back to the term, multiplicity, the sum to the degree of the polynomial. This is the fundamental theorem of algebra. So we have to, our basis will be the sum of the degree in this case. So that means our degree is 5 with all zeros at x minus 5, x equals negative 5, x equals 1, and x equals 4. That means we have real zeros here, 1, 2, 1, 1, and 1. So that means the real zeros, we have 3. And the degree is 5. That means the non-real should be 5 minus 3. That would be 2. So the non-real zeros is 2. When you sum that up, is equals to the number of degree. Okay? The degree is 8. With the real zeros, x equals 0, you have 1. X equals 2, and x equals 3. But x equals 2 has a multiplicity of 4. That means this is 4, and we have 1 multiplicity. That means, all in all, the zeros that we have, the real zeros, will be 1 plus 4 plus 1, that is 6. So the non-real zeros will be 8 minus 6, because the degree is 8, is equals to 2. Alright? Simple as that. So complex zeros. A polynomial of degree n is exactly the n complex roots. Remember, the complex zeros are the real and non-real zeros. Complex. When counting multiplicities, complex refers to real and non-real zeros. Okay, let's do. How about if we look at in the terms of a sketch, a graph? You're asked how many real zeros and non-real. Okay, let's have a degree of 2. All right. So, it's when it's quadratic, it either point up, but ends, or point down. So in this case right here, I have the points here. So those are the zeros. So I have 2 zeros. So that means, since the sum is 2, that means my non-real zeros is 0. I have none. Nothing. Non-real. So 2 plus 0 is equal to the number of degree. In this case, it touch. It just touch, like it bounced. So that means, what did we say? There are 2 values right here. Like in this case, there are 2 values as this point gets closer. So when it gets closer, so that means in that point right there, there are 2 zeros, or 2 intercepts that is happening there. That means you have real zeros 2, and the non-real is 0. Okay? You have to add up. Add. Next, about this. It did not hit the x. Nothing. So that means the real 0 is 0. Right? It's quadratic, then the non-real would be 2. 0 plus 2 would equate to the number of degree. Cubic, that's the degree of 3. All right. So if the graph is a cubic graph, I have it here, 3 dots, 3 points. It intersects at 3 points. So the real zeros is 3. Remember the degree, it should sum up to the degree, so 3 plus 0 is 0. Okay. In this case, this is still a cubic graph. It intersects at x only one time, so that's 1, 0. So 3, it should sum up to 3, so the non-real is 2. 1 plus 2 is equals to 3. So in this case right here, we have 1. In this case, when it touch, that means there are 2. Remember the 2 points, when they get closer, they just touch. So the real zeros here is 3, and the non-real is 0. So 3 plus 0 is 0. All right. So let's look at the last term that we have to deal in this lesson right here. We have the degree. Degrees of polynomial, that is the degree of a polynomial of a function, is the highest power in the independent variable in its expression. So to determine the degree of a polynomial, if that is, it happens that you are given a table, there is no graph, and you are asked to find the degree of this polynomial function, all you do is to get the successive differences of the output values over it should be the equal interval input values. I have to make this one right here. I have to change that to over equal interval input values. So the degree is equal to the least value n, for which the successive and degrees are constant. All right. Okay. Let's do this. We'll try to inspect first our input values if they are equally interval. So they are interval of 1, 1, 1, 1. So they are equally interval. Right? So we'll do first, let's get the difference now of the output. 55 minus 15, then you have 40. 15 minus 1, you have 14. 0 minus 0, 1 minus 1, that's 0. 1 minus 3, that's negative 2. This is first difference. What have we observed after subtracting, the output values interval? We come up with all different numbers. 40, 14, 0, negative 2. So we'll try to do another difference. By subtracting 40 minus 14, you have 26. 14 minus 0, you have 14. 0 minus a negative 2, that's 2. This is the second difference. It's still you come up with different numbers. We'll try again. See this? 26 minus 14, that's 12. 14 minus 2, that is 12. So at last, we in the third difference, which are subtracting by the consecutive second, we are able to get a constant of all the same, and they are all the same number, 2. Because of the third differences are the first to be constant, then the degree of the function is 3. Okay, this is the third difference, right? Third difference. So at this point where it has a constant value now, so the degree of the function is 3. Okay? Consider, let's have this number. Alright, let's do this. Consider the polynomial function h of x equals x minus 3 and times the quantity of x squared minus 4x plus 5. State the zeros h of x. So using the zero product property, if you remember that in your algebra 2. So what do we do in the zero product property? We set each factor equal to 0. So the first factor, x minus 3, I will equate that to 0. So x would be equal to 3. And the second factor, x squared minus 4x plus 5, you have a quadratic function there, is equals to 0. So if we try to factor this out, we always remember in factoring, we always look at the last term. Our last is 5 and the factor of 5 is 1 and 5. So in such a way that we have, when we add the two, it should be the sum, or it come out with the middle term. So if we try, I will show it to you. If we try like x, I'll have a factor here. If the middle term, let's say 5, and this is positive. Now, take note the last term is positive. So I have to make this into a positive. Alright, so I have to change that into a positive. I mean a negative. Because a negative times a negative would come out a positive. Alright, so what happened if I do that? I have a negative 5x and minus 1x. I could have a negative 6x in the middle. So it doesn't give me a negative 4x. That means I cannot factor that out. I cannot do this. What the other thing I could do is use the quadratic formula. Okay. Remember the quadratic formula? We can get the roots from using the quadratic. So what is the quadratic formula? You have x equals negative b plus and minus square root of b squared minus 4ac over 2a. Now, what we're going to do first is I have to bring this up. We'll have to identify the a, 1, b is negative 4, and c is 5. Right? Then substitute this value to the formula. B is negative b, so it's negative 4 plus and minus negative 4 squared minus 4 times 1 times c, which is 5, over 2 times 1. Okay, so we have our quadratic formula and we have substituted. So what we're going to do is to simplify. So x would be negative negative, that's a positive 4, plus and minus. Negative 4 squared is 16, minus 4 times 1 times 5, that's 20, over 2 times 1 over 2. So 4 plus and minus 16 minus 20, that's negative 4 over 2. We can, cancel out x and 4. So we have 2 plus and minus. Remember, in a complex, we have a negative value under a radical sign. Then we have an imaginary number. All right? So that's would be equal to 2 plus and minus I. So what are your two values of x? X will be 2 plus I. Okay? The other one is x is 2 minus I. And the other root that we have is x equals 3. These are the zeros of the function h of x. Okay? That's how you have the zeros there. Write the equation. Write an equation wherein h of x using linear factors. Okay. So what would be that equation there? In part A, we found that x is equals to 3, x equals 2 plus I, and x equals 2 minus I. So we can apply the zero property, product property, in reverse. I will write it here to have a space. Zero product property. Let's do the reverse way. To rewrite three solutions, or to rewrite the solutions as factor. So starting at x equals 3, okay, what we're gonna do, x equals 3, I subtract 3 from both sides. So I have x minus 3 equals 3 minus 3, and that would be x minus 3 equals 0. Okay? Is equals to 0. And I do the second one for x plus 2i. Okay? I will do x plus 2i. I mean 2 plus I. Oops, sorry. X is equals to 2 plus I. So subtract 2 and I from both sides. So if I subtract 2 and I, let's say x minus 2 and minus I would be equals to 2 plus I minus 2 minus I. Right here. So this will be 2 minus 2, I minus I, that will become 0. So in other words, x minus 2 minus I is equals to 0. Okay. For the third one, 2 minus I. For 2 minus I subtract 2 and add I from both sides. So x subtract 2 and add I. Then 2 minus I subtract 2 plus I. In order to cancel out and make your right side equal 0, That's the time whether you subtract or you add the I, the imaginary number there. So you have, we cancel that out, it will be x minus 2 plus I equals 0. So you have the zeros now. So what will be your equation of h of x using the linear factors? Okay, so we have the first one, which equate to 0, is x minus 0. The second one is x minus 2 minus I. And the third is x minus 2 plus I. This is your equation. Alright. For using the linear factors. I hope that is clear so far. 2. Given the polynomial function p of x is x squared times x minus 4 times x plus 5 without graphing. Okay, without graphing. Describe the behavior of the graph near the 0 when x equals 3. Okay. First of all, we have to consider the multiplicity of the 0 in question. Multiplicity of x equals to 3. So it's a 0 from here. Okay, it has a multiplicity of 3 because you have that x equals 3. It is a 0 with multiplicity of 2. Okay. So that would be our basis of our observation. So even a multiplicity, what does even multiplicity means? That the function will touch. Okay? The function will touch. So you are asked to describe. So the function will just touch. Remember the one I've shown you? And then what happened when it touched the x-axis or bounce at x equals 3. So it just touch at x equals 3 and then turn. So touch, bounce, or whatever you have, and then turn and continue. In the other direction. Right? Continue in the other direction. Meaning it will not cross the x-axis at this point. Okay? It will not cross the x-axis at this point. So, if you have like this, if we try, make a sketch, but we're not asked to graph, but we're asked to describe. So, I'm just curious what happened if we graph. This will be x equals 4. This will be x equals negative 5. This will be x equals negative 3. Okay? So if we have x equals 3 or negative 3, so what happened when it crosses the graph? Alright. Let's make a summary of all the terms we did. So how many terms do we have? 1, 2, 3, 4, 5. Multiplicity of 0 is the number of times that its corresponding factor appears in the function. How many times? Even multiplicity, the function touches or bounds the x-axis, that the zero then changes direction. When it's odd, it crosses the x-axis at 0. So complex roots come in conjugate pairs in the form of a plus bi and a minus bi. Successive differences by subtracting consecutive y values, the degree of polynomial is found by identifying which successive difference is constant. At what successive difference is constant? At what? Is it at the first, at the second, the third, the fourth, and so on? All right. So much with that. We'll have more problems and solutions of this lesson. All right. So we'll do that in the next video. So let me say this: if I can do it, so can you. So please don't forget to hit the like button and hit the subscribe button and share, please. Okay, thank you.